Hello and welcome to today's class. In today's class, we'll be talking about strength of material. What does it mean when we say strength of material? Now, the idea is very simple. Now, strength of material, by definition, is the maximum resistance. Strength of material is the maximum resistance a material. Strength of material is the maximum resistance which a material can offer to the externally applied load, meaning the interaction between the externally subjected load and internally generated force of adhesion and coercion. Okay, considering this material, beam, in this case, we have a beam. This is A, this is A, this is B. This beam being subjected to a load, let's say point load. Right? Now, from the definition of strength of material, we said the maximum resistance a material can offer under the application of external load. Meaning, for this load being subjected to this beam, there is a certain point where this beam can deflect, where the maximum deflection can occur. What we are saying is that the deflection, which is the elastic curve, from this point to this point is the deflection, and it is denoted by Y. Meaning that the maximum resistance this body or material, which is the beam in this case, can withstand, can stop, right? If the load is more than the resistance the beam can offer, it means that the beam, there will be a shearing load. Hence, the beam, in a layman term, it means the beam will break. So there will be a shearing. So that's what we are saying by the maximum resistance a material, a body can offer under the application of external load. Alright, there are these terminologies we'll be using in strength of material. The first one is load. What is load? When we say load, by definition, what is load? A load is any external force. A load is any external force acting on a body. A load is any external force acting on a body. Right? What we have here, this illustration, this is a load. This is a point load. It is acting on this beam, which is a material, a body now. Now, classification of load. We have different types of load. We have the tensile load. We have tensile load. We have compressive load. We have shearing load. We have twisting load. We have bending load. But let's look at these first three. Let's see what it means when we say tensile load, compressive load, and shearing load. From the word tensile, for the first one, when we say tensile load, from the word tensile, it means elongation, increment, increasing, right? This is the type of load. This is the type of load whose effect is to increase the material. This is the type of load whose effect is to increase the length of the material in the direction of its application. In the direction of its application. Consider this material for tensile load. Consider this material. This is A, this is B, C, and D. Now, this material, we are applying a tensile load. When we say tensile load, it means force in terms of pull. So this is what we have. We are applying this force, denote it as P, and we know force is in kilonewton. kilonewton. P in kilonewton. Now, when this force is being subjected or it is acting on this material, then from the idea of tensile load, it means there will be an increase in length. From the definition, this is the type of load whose effect is to increase the length of the material along the application. All right. Now, for compressive load, it is synonymous to this, but vice versa. For compressive load, the load whose effect is to decrease the length of the material in the direction of its application. Now, when we say the direction of its application, let's see what it means. Let's considering these two case. For case one, let's use this diagram. When we have this material A, B, C, D, applying a compressive load, meaning that there will be a shortening in length of this material. But in that definition, observe, they said to decrease the length of the body or to decrease the length of the material in the direction of its application. Now, the question is, this load is applied in horizontal manner, right? Meaning any shortening that will occur here will also occur in a horizontal manner. What if we have call it case 2? What if you have our material? Now, let's say we have different type of structural member. Let me use column now. Let's say we have column, or we have our cylinder that we all are familiar with. Now, applying compressive load. From here, there will be a shortening in length. Shortening in length. But what I want us to deduce from this place, the way the shortening in length will occur in case 2 will be different from case 1. Why? Because in case 1, the load is applied in horizontal direction, while in case 2, it is applied in vertical direction. So the key word in that definition is there will be an increase or decrease in length of the body in the direction of its application. So that's the key word. Moving on to the next one, we have shearing load. What does it mean when we say shearing load? All right, step down, please. By definition, the load whose effect is caused. The load whose effect is to cause sliding of one face of the body relative to the other body is called shearing load. Now, what it means, okay, this is a compressive load. Now, shearing load. For shearing load, let's say we have a fixed boundary. We have our material. This is A, this is B, this is C, this is D. Relating this to X and Y axis, we can say that this material ABC is giving the shape, or is a right angle triangle. Let me put it that way. Meaning it is inclined at 90 degree, right? 90 degree. Now, we are applying this force. Apply this force for speed in kilonewton. You know, the angle here now is what? We said 90 degree, right? Now, applying this force of P kilonewton, there will be a shearing load the 90 degree will change. There will be a new degree. Let's say we have something of this. We have something of this. Then from here, from the initial axis up to this one, this is A prime, this is B prime. We have phi or degree, be it theta or phi, still degree. We also have phi here. So what it means, the idea of sharing load is that after applying this force, there will be a sharing load, and this sharing load will cause another angle. There will be a change in degree. There will be a change in degree. So that's sharing load. All right. For twisting load, we said we have twisting load, we have bending load. By definition, bending load, the load whose effect is to cause a degree of curvature, or bending in a body, to cause a degree of curvature or bending in a body. Whereas twisting load, the effect produced by two couples applied at opposite ends of the body so as to cause one end to rotate about its longitudinal axis relative to the other end are called twisting load. For dead load and life load, dead load, what it means when we say dead load are static load, right? For example, a typical example of dead load, a construction building is a dead load. Why? Because it is unmovable, we can't move it, it's static. All right. For life load is the idea of life load is fluctuating load. Next one is stress. When a material is subjected, when a load is being subjected to a material, stress is said to be induced. You understand? Stress will be induced. But let me give you what the definition means here. They said stress may be defined as the internal resistance. Stress may be defined as the internal resistance per unit area of cross section offered by a body against deformation. We said stress is denoted sigma. We denote stress as sigma. And it is in Newton per meter square. From the definition, mathematically, stress is equals to the force over area, and force is measured in what? Newton, while area is in what? Meter square. Meaning we have Newton per what? Meter square or Pascal. So we have different types of stress. We have tensile stress and we have compressive stress. We have tensile stress, we have compressive stress. Tensile stress. When an axial pull is applied on the cross-section area of a body, the stress induced is known as what? Tensile stress. Earlier we said that stress, when a load is being subjected to a body, we said stress is said to be induced, right? Now, we said we have two types of stress. We have the tensile stress and we have the what? Compressive stress. Now, the idea is, earlier we've seen that we have different types of load, which is force. The first one is what? Tensile load, and the second one is what? Compressive load. When we apply a tensile load to a material, the material will increase. The tensile load in this case is what? Load in form of pull, right? To increase the length, right? Similarly, compressive load is what? To shortening the length of the material. Now when we now say we have tensile stress, what can we deduce from there? It means when this tensile load is being applied to the material, the stress in that case is what? The stress induced is what? Tensile stress. You understand? Similarly, when compressive load is being applied to a material, the stress induced is what? Compressive stress. So that's how it works. Any questions so far? No question. I said mathematically, stress is given out from the definition using defining stress mathematically. We said it is the what? What do you have on your note? In your note rather. It is the what? Internal resistance per what? Unit area. Meaning the force per area, which is what? Newton per meter square, or what? Pascal. Also, the next one is strain. The next one is what? Strain. The next one is strain. Strain. When we say strain, what does it mean? This is how you denote your strain. Strain, it is the ratio. Strain is the ratio. Strain is the ratio of change in length to the original length. Strain is the ratio of change in length of a body to the original length of the body or material. What it means is that also we have tensile strain, we have compressive strain. For tensile strain, consider this your material. Then we apply the force in form of pull. This is the initial length. And when your material is being subjected to load in form of pull, then the length will increase. Meaning there's a new length. Then from year to year is what? Change in length. Then how do you determine the strain of this? It means strain is equals to what? Tensile strain now. Tensile strain is equals to what? The change in length over the what? Original length. And change in length is in what? Meter. Also, length is also in what? Meter. Meter cancel meter. It is dimensionless. It has no unit. Similarly, for compressive strain, same idea but the reverse now. It will now be what? Strain. It will now be we applying. Which type of force I'm going to apply here? What's the type of force? Is it, this one is form of pull now. This one will be what? Push. Force in terms of what? Push, right? If this is the original length, then there will be a shortening in length due to the applied force. Then we have this, Abi. Then from year to year is what? Change in length. Then how do you calculate the strain of this? It means that the strain now, compressive what? Strain will be equals to what? The change in length over the what? Original length. There's no in for that also. Any questions so far? Any question? All right. Rooks Law. Rooks Law. Rooks Law. Rooks Law. The Rooks Law we know from our basic class or preliminary class is that the extension of a material or the elongation of a material is directly proportional to the what? Applied force. Abi? He said that Rooks Law, meaning that force is directly proportional to what? E. Introducing constant, we have that F is equals to what? Ke. Call this equation 1. Where F is the what applied force, E is the what extension of the material, while K is the what spring constant or stiffness. This is the Rooks law in terms of force and extension. Now, Rooks law in terms of strain, in terms of stress and strain. Rooks law in terms of stress and strain. And it says that when a material is loaded within limit of proportionality, the strain is directly proportional to stress produced by it. Mathematically, we have that stress sigma is directly proportional to what? Strain. Alright. Any question on that? We said that Rooks law in terms of what stress and strain means stress is directly proportional to the what? Strain. Then this is it mathematically. Then variation. This sign, proportionality sign, has to go away from variation. Then the constant in this case now is capital letter E, meaning stress is equals to what? E dot strain. Divide both sides by strain. What do you have? You have that. Call this equation 1. Then from here, divide both sides by strain. You have that E is equals to what? Stress over what? Strain. Call this equation 2. What you have here, this relationship is called Young modulus or modulus of elasticity. Young modulus or modulus of what? Elasticity. From there, from what you have here, you can define Young modulus as the ratio of stress to what? Strain. Okay? We said it is what? Young modulus or modulus of elasticity. Right? From here, the next thing is what's the unit of Young modulus? You know, we said that stress is what? Newton per meter square, and this one is what? Dimensionless, meaning that Young modulus still has its unit to be what? Newton per meter square. Now let's do some mathematical expression of Young modulus. This is Young modulus in terms of stress and strain. Now let's see Young modulus in terms of force, area, length, and the likes. From equation 2, we said that Young modulus E is equals to what? Stress over what? Strain. And we know that stress is equals to what? Force over area. Right? Call this equation 2. We also know that strain is equals to what? Change in length over what? Original length. Call this equation 3. Substituting equation 2 and 3 into equation 1, we have that Young modulus is equals to what? Force over area divided by change in length over what? Original length. From here, division will change to what? Multiplication. We have that F over A times L over what? Change in length. Meaning that Young modulus E is equals to force times length over what? Area times what? Change in length. In what? Newton per meter square. Where F is the applied force, F is the force, L is the original length or initial length, A is the cross-section area, while change in L is the change in length, while delta L is the change in length. Any questions so far? No question. Alright, let's take down this example. Before taking down this example, note, we said we have Young modulus, Abi. We said Young modulus is the same thing as what? Modulus of what? Elasticity. We also have modulus of rigidity. modulus of rigidity, modulus of rigidity, modulus of rigidity. That modulus of rigidity now, the difference is that modulus of rigidity, modulus of rigidity is denoted by G, letter G, letter G, or you say N or C. So modulus of rigidity G is equals to shear stress, all over shear strain. The ratio of shear stress to shear strain is what? Modulus of rigidity. Then shear stress is tau. Then shear strain is represented as this. So take note of that. Now take down this example. Are we together? Any questions so far? A square steel rod 20 mm by 20 mm, a square steel rod 20 mm by 20 mm in section is to carry an axial load, in brackets compressive, of 100 kilonewton. Calculate the shortening in a length of 50 mm. Calculate the shortening in a length of 50 mm. Take E, that is Young modulus. E equals to 2.14 times 10 raised power 8 kilonewton per meter square. 2.14 times 10 raised power 8 kilonewton per meter square. Solution. What are the given parameters?
Area.
Okay, we are giving solution given what are we giving from that question? We are giving area to be what? 20 mm by 20 mm. What else?
Force.
We are giving force to be what?
100 kilonewton.
100 kilonewton compressive, right? And what? We are giving E, Young modulus, 2.14 times 10 raised power 8 kilonewton per meter square. We are giving the length to be what? 50 mm. What are we asked to calculate? Okay, you have to calculate the change in length, that is the shortening in length. Now, how do you go about this? From here, recall from Young modulus, we said that Young modulus is equals to force times length all over area times what? Change in length. From this equation, then from here, make change in length the subject of the formula. What do you have? That will be E times A times change in length equals to what? FL. Divide both sides by what? EA. Then you have that change in length is equals to what? Force times length all over Young modulus times what? Area. But observe, your Young modulus is given in what? Meter. Then your area is given in what? Mm. What it means is that you should convert area, which is in mm, to meter, which is the unit of Young modulus. In essence, what we are saying is that whenever we are given a question, our consideration should be on what? Young modulus. The units Young modulus have will be the respective units that you'll be using as far as that question is concerned. So let's get this done. Area 20 times 10 raised to power minus 3 times 20 times 10 raised to power minus 3 will give us area in meter. Then what's the value? We said we want to convert area to meter. 20 times 10 raised to the power of minus 3 times 20 times 10 raised to the power of minus 2. We have 4 times 10 raised to the power of minus 4 meter square. Any question how we get that? Any question? We converted area, which is in mm, towards meter. Then the next thing we need to do is to substitute the respective value. We know that force is what? 100 kilonewton. We have 100 times length. Length is given. Also, we need to convert length to what? Meter. Meaning 50 times what? 10 raised to the power of what? Minus 3. We have 0.05. 0.05 over Young modulus is given to be what? 2.14 times what? 10 raised to the power of 8 times area. We've calculated our area to be this. We have 4 times 10 raised to the power of minus 4. Now, input this value in your calculator. What do you have? So therefore, change in length is equals to, I will do yours, I'm going to do my own here. I have 100 times 0.05 over 2.14 times 10 raised to the power of 8 times 4 times 10 raised to the power of minus 4. What do you have? 5.84 times what? 10 raised to the power of minus 5. 5 what? No. 10 raised to the power of 5 meter. Your answer is in what? Meter. You can as well as convert your answer to what? Millimeter. Meaning that from here, we've calculated the value of change in length to be what? 5.84 times 10 raised to the power of minus 5 meter. Now, your change in length in mm will be 5.84 times 10 raised to the power of minus 2 mm. Then this is your final answer. This is change in length in meter, change in length in what? Mm. Any question? All right.